All right, let's take a look at two more problems just to see if we've got the right idea on how to do this. So here we have Bill heading off to school. It's going 5 meters per second. 5 minutes later, his mother discovers he forgot his lunch. She gets in the car. Okay, cars normally aren't moving, so she has an initial velocity of 0, and she accelerates. How long does it take her to catch him, and how far does she have to go? So two questions we have to answer here. Again, first thing that we want to do is draw out that motion map type line and identify the quantities we know about each of our moving objects. So there's our line, and we'll do Bill in green. He has a constant velocity, and he's going 5 meters per second. He has no acceleration. Okay, those dots are supposed to be evenly spaced. We're going to say each dot is 1 minute, moving at a constant velocity. So Mom, down here, has an initial velocity of 0, has an acceleration of 1.5 meters per second. So Mom's sitting around the house for 5 minutes, so we show that by giving her 5 dots, stationary. Then she starts out moving and accelerating in the hope of catching Bill. 5 minutes after our scene opens, Bill is here. So we can figure out how far he traveled before Mom realized that he was gone and didn't have his lunch. So the distance he traveled in that 5 minutes is his velocity, 5 meters per second. Okay, now we got to switch from minutes to seconds here. 60 seconds times 5 minutes, so we have 300 seconds. So that means that Bill has gone 1,500 meters by the time Mom finally gets going. And so the equation to figure out how far Bill has gone from home to when Mom catches him is going to be that 1,500 meters that he's traveled already, plus his actual velocity, plus his velocity times time. Mom's displacement equation is going to be like our patrolman in the other problem. She's accelerating, so we're going to use a kinematic equation with that in it, 1/2 acceleration times squared. Her initial velocity is 0. So if we realize that, we can make sure that we cross it out because that term goes to 0. Again, if Mom catches Bill, we can set the equation for Bill's displacement equal to the equation for Mom's displacement. So for Bill, we have 1,500 meters plus 5 meters per second is his speed times t, and Mom is going 1/2 acceleration. Her acceleration is 1.5 meters per second squared times t squared. As we did before, we're going to rewrite it in a quadratic equation format, so it'll look like this. Now we have it in quadratic formula, and we can figure out what time is. We have time, in this case, equal to 48.2 seconds and negative 41.5 seconds. Again, we have a positive time, negative time. Life is easy. So does Mom catch Bill? Answer is yes. We have a positive time. So it's a workable and solvable problem. How far does she have to travel? Well, we take the time and we put it back into her displacement equation, and we figure out how far she had to go. So displacement for Mom is 1/2 times 1.5 meters per second squared times 48.2 seconds, and square that, and we get the displacement, how far she traveled. If we discount sig figs, 1,742 meters. 1,740 meters or 1,700 meters, depending on how many sig figs you want to include. So that's how we set it up. Again, the pattern is draw the line. Identify what quantity each object has. Assume they catch each other, and set the two displacement equations equal to each other, and then you can usually solve for time and go back and plug it into the equation to find a distance. Okay, so here we've got Fred and George. Again, first thing we're going to do is draw the line. Identify where they are and what we have. It also says that Fred is 5 meters behind George, so we can identify that. So here's Fred, George, and this is 5 meters. So George has an initial velocity of 0 because he's starting from a standstill. He has an acceleration of 1.25 meters per second squared. Fred has a velocity of 4.75 meters per second, and he has no acceleration. He's running at a constant velocity. So if we mark our distance from the furthest backmost point, so right here, we want to find out how far George travels from that point when Fred finally catches him. So we're looking at George to go all this way. So his displacement is going to be the 5 meters head start he has, plus he's accelerating, so we're going to go 1/2 a/t squared plus vit. Initial velocity is 0, so that term is gone. Fred's displacement equation is going to be just his constant velocity times time, so just v times t. We're going to set them equal to each other to see if Fred does catch George. We have to answer the second question here before we can answer the first question. So we're going to set the equations equal to each other. Again, we're going to rewrite it so that we got a quadratic Solving for t, we get 6.33 seconds, and we get 1.26 seconds. Two positive times. Okay, so we have to figure out which time is the one that we want to use. So, because we have two positive times, does Fred catch George? Yes, absolutely. In fact, he makes contact with him twice. How long does this take if he does catch him? Well, which do we take first? If you know anything about relay races, you know that you want to have a handoff in a particular region. So we would want to have the handoff at the first or smaller time rather than the second time. So we're going to try with our 1.26 seconds and see if that gives us the answers that we need. The third part of this question, how far from where George starts does this occur? Well, let's use George's equation, and he starts from a standstill. So his displacement equation is just the 1/2 at squared part. So we have 1/2. His acceleration is 1.25. T is 1.26. I'm going to square it. So that happens 0.99 meters from where he started running. If we wanted to check the other time just because we wanted to be really sure, we do the same thing, same kinematic equation. 1/2 acceleration doesn't change, 1.25. This time we're going to use the time of 6.33 seconds. Square that, and we find out that the second time they make contact is 25 meters down the track. So we can find out where both of these exchanges occur if both of them keep running at their initial rate. So last question, if the handoff zone is 10 meters long, so if we go back and look at our motion map type of diagram, so here's Fred, here's George, this is the 5 meters head start. If the handoff zone, so George is standing at the beginning of it, is 10 meters, and what we saw up in letter C is that George makes contact with Fred, or Fred makes contact with George, at about 1 meter after George starts, that's going to be about right there. That's definitely the handoff zone. So, is the handoff legal? Absolutely. And so that's how we're going to work with problems where we have two objects moving at the same time. Draw the line, identify what values each object has, figure out where they start, and figure out what the distance equation, the displacement equation is for each of them. Assume they meet and set those displacement equations equal to each other.